We're now going to discuss conductors, branch circuits, and overcurrent protection devices. One of the duties the project inspector is going to fulfill is to make sure that all the materials that are delivered to the project site have been approved and there is documentation supporting those particular devices. Part of this function is going to be verifying that any overcurrent protection devices are rated with the appropriate voltage and amperage for each of the circuits. This requirement is reiterated in Article 240.83 A and E. Also, it's important to determine the proper overcurrent protection device and interrupter ratings. This is identified in Articles 110.9 and 240.83C. It's also important to verify proper overcurrent protection device size for conductor protection. This is identified in Article 240.4D and Table 310 15B16. I would caution project inspectors, again, as we've done many times through this process, to be very careful to not become a designer or to not migrate into a designer role. Your function as a project inspector, particularly with the electrical installations, is to be sure that the installations comply with the plans, comply with the specifications, comply with the submittals that have been approved by the design team members. Obviously, there are seismic bracing and support and anchorage components that will be reviewed and approved by DSA engineers. However, when it comes to the nuts and bolts of electrical installations, again, I would just caution you to not spend too much time in the tables. The tables are provided as backup information for project inspectors, but the tables are utilized primarily by design professionals during the design phase of projects. Arc energy reduction is a very important topic, again, from the perspective of providing personnel safety for service personnel, and Article 240.87 addresses situations where the overcurrent protection device is or can be adjusted less than or equal to 1200 amps. Documentation is required to be available identifying the location of the circuit breakers, and the overcurrent protection devices must have approved methods to reduce their clearing time. Okay, remember, what are we supposed to have going off in our heads right now? Read every word and every symbol on every plan and specification sheet for every project every time. Now, this particular excerpt from a plan drawing shows a couple of interesting, or a few interesting things, all of which obviously needs to be inspected by the project inspector. If we look at the very top note, it says clean, service, and test substation in accordance with manufacturer's recommendations. Now, obviously, this is a task that is going to be completed by the contractor, but the project inspector needs to verify that this task was actually completed. So, what you're going to need to do is obviously get a copy of the manufacturer's recommendations for cleaning, servicing, and testing that particular substation, which is located in the boiler room, and it's a 4160 volt primary with a 500 kVA, 120, 208 volt, 3-phase 4-wire secondary, 1600 amp secondary distribution section. Obviously, one of my first recommendations would be when you go into this area, keep both hands in your pockets. Do not touch anything. Look to make sure that the required working clearance spaces are provided. If they are not, remind the contractor that they need to do that before you even get near this equipment, before you even get near the area, and provide any type of monitoring if they're cleaning and testing this particular substation. Another couple of very simple tasks that are included in the words on this drawing are replacing some existing 300 amp or an existing 300 amp 3-pole breaker with an 800 amp 3-pole breaker, and removing a spare 250 amp 3-pole breaker and replacing it with a 600 amp 3-pole breaker. There is also some information on the bottom portion of this sheet that identifies an energy management system and some work associated with that. So again, it's very important that project inspectors get used to reading every single word and symbol on every single plan and specification sheet for every project every time. And again, the intent is to make sure that the picture that is painted of the project by each of these pieces of information that are provided becomes clearer and clearer to the project inspector every day. Here we go again. Read every word and every symbol on every plan and specification sheet for every project every time. Now this particular page shows a panel schedule, and the panel schedule contains a tremendous amount of information. And it is certainly worth identifying some important points that are actually shown on this particular drawing here. Let me start by saying that you don't need to become an electrical contractor or an electrical engineer to become familiar with and comfortable with deciphering the information that is on panel schedules. But it's an extremely critical part of gaining enough information to be able to effectively inspect that the panel installation and all subsequent connections made to the panel comply with the drawings. So let's start by just saying, in general, you've got the actual panel name, which is located here, or the ID number, which is KD1D, and the location of this panel, which is identified here, which is in the kitchen. Now there's also very important panel and breaker information. So we'll start with some of the panel parameters, which are located down in this lower section of the panel schedule. As you can see here, it identifies the name and the location of the panel, as we've just discussed. The parameters such as the size, which is 125 amp, the voltage, which is 120, 208 volts. It's 3-phase, 4-wire. The main is a 125/3 MCB. The breaker AIC rating, remember the AIC is the Ampere Interrupting Capacity, is 10,000 amps. It has a copper bus, a standard neutral, and a standard ground. The mounting is flush, and the choices here would either be flush or recessed, obviously. The enclosure rating is a NEMA 1, and it's fed from panel MDS-KD. This other information here, the connected KVA, the connected amps, the CEC KVA, and the CEC amps, is primarily design criteria and summaries, which are basically taken from the center section of this panel schedule, which identifies basically power provisions, apparent power provisions that are corresponding with the loads that you can see for each of these circuits. And we'll talk in more detail about those. And there's also, excuse me, very important notes that are located over in this lower right-hand section. And also the code descriptions for each of the codes that are identified in each of the sides of this panel schedule. Now, the way the panel schedules are set up, it's basically a listing of breakers, and you have your your odd numbered breakers identified on the left-hand side of the panel schedule, and the even numbered breakers located on the right-hand side of the panel schedule. And if we just look at this very first entry, the code is K, which stands for the kitchen equipment. It's actually a griddle number 59 and a steamer number 00. Again, we're not concerned with the loads, but we are concerned with the fact that it's a 20 amp single pole breaker and it's attached to circuit number 1. Now if we come across to circuit number 2, we can see that circuit number 2 is for the ice maker, which is also in the kitchen, and it's a 20 amp 2-pole breaker. So you can see here that 2 poles are actually taken up here, and the circuits that are involved are circuits number 2 and 4. So this 2-pole breaker is connected to the A phase and also the B phase. If you look at circuit number 1, it's only a single pole breaker, so it's only connected to one phase of the incoming power, which is the A phase. So again, I don't want to belabor too much of this, but there is a lot of important information on here relating to the panel itself and also the breakers. And you can see that for breakers, we've got circuit numbers that are identified, again, on each side. We have the actual breaker numbers, okay, the breaker parameters, for instance, 20 amp single pole, another 20 amp single pole, and as we scroll down here, these all appear to be 20 amp single pole breakers, and they tell you exactly where they come from, where they go. On this other side, we see a variety. We've got some 20 amp double pole breakers, we have some 20 amp single pole breakers, we have spares, so the breakers are going to be provided, but they're going to be spares. And then here we have empty spaces in breaker locations 22, 24, and 26. And then as we continue down, we can see there's some additional equipment. Again, if we want to check the code H stands for HVACR equipment, right? Right here. And it's not uncommon to see exhaust fans and fan controls. This particular breaker here is a 15 amp 3-pole breaker, and you can see it's fed from circuits, or it is circuits 32, 34, and 36. So you've got a 3-pole breaker, 15 amp, so you would expect to see 3 breakers with tie bars across them. Now also, if we look at these notes down here, you can see that they have a special note that says for breakers 32, 34, and 36, and also 38, 40, and 42, they are required to be HACR rated, which obviously stands for, or should stand for, heating, ventilation, air conditioning, and refrigeration. So it appears there's a typo in there. Additionally, if we look at breaker number 10, it's required to be painted, the handle painted red, and provided with a block-on device. Now what does that tell us? Well, if we look at breaker number 10, this clearly says fire suppression system, number 47. So this is going to tie in with other fire life safety requirements that we'll address later in the presentation. But again, not to belabor too much of this information, It is extremely important that all project inspectors review every word and every symbol on every plan and specification sheet for every project every time. And once you do this a few times, you're going to become more familiar and more comfortable with deciphering the information that you need to monitor and review and verify has been installed correctly by the contractor. This slide is pretty much just a summary of all the information we just discussed on the previous slide. But again, let's go over this again. There's a ton of important information that's provided on the panel schedule. Certainly, it's important to review to become familiar and comfortable with deciphering the information that's provided. Some of the general information is the panel name, ID number, and its location, and there's specific panel and breaker information. For instance, panel parameters, the name, the location, the voltage, the phase, how many wires, the AIC rating, what type of bus, what type of neutral, what type of grounding, what the mounting considerations are, whether it's flush or recessed, the enclosure or NEMA ratings for the panel. Also, more design-related information such as the loads of each of the circuits, the power that's provided to each circuit, and important notes. Breaker parameters include circuit numbers, breaker numbers, a description for each of the breakers which identifies the name and the location of the protection, the capacity of the breaker and the number of poles associated with the breaker, including code descriptions that provide additional information for locations. These two photographs provide a couple of looks at a standard single pole breaker. And this particular breaker, I know it's difficult to see, but it actually has information associated with it relating to the AIC. You can see that it's a 20 amp breaker, and it is a 10,000 amp AIC rating. These two photographs show an image on the right of a typical two-pole breaker, and as you can see, if you look at the handle, you can see that there's definitely a tie bar attached. And the tie bar itself makes sure that when these breakers are shut off, they're shut off simultaneously, and when they're turned back on simultaneously, because that's a critical function of the equipment or the components that are energized upstream of this particular breaker. What we have on the left is it's a blow-up view of more information that's located underneath the actual handle, and it basically identifies that it's 120/240 volts AC. You can tell that these are two 30 amp breakers, and each of the breakers has a 10,000 amp Ampere interrupting capacity. These two images show a couple of pictures of some fuses. Now these fuses are rated at 250 amps. I know you can't see it too well here. Here's a little blow-up picture of what you can't see too well. But again, what it shows is these are 250 amp fuses. And the AIC rating on each of these fuses is 200,000 amps. Now the thing that I want to have you pay special attention to is the fact that if you look at these particular contacts, this one here on the bottom and this one here on the top, you can certainly see where there was a dramatic ground fault across this particular leg of this circuit. So much so that it's burnt away a large portion of this bottom contact, and you can see where it's basically attempted to spot weld the top contact. And again, it served its function. What it did was it opened up so that this fault current stopped flowing across this particular fuse. We're going to change speeds here and talk about circuit identification, specifically multiple circuits existing in an enclosure. When multiple circuits exist in an enclosure, beginning with the previous code cycle, all of these circuits needed to be tied together, separate circuits, so that they're grouped together specific to their circuit, which includes their neutral. And the whole purpose for this is so that service personnel that would happen to open an enclosure and see a ton of wires understand which neutrals go with which ungrounded connectors, whether it's a multi-branch circuit or a single branch circuit. So the requirement is identified in Article 200.4b of the California Electrical Code. And basically, to reiterate, the separate circuits must be identified by grouping the grounded conductor, which is the neutral, with all ungrounded conductors in the circuit. And this applies to enclosures where more than one circuit or more than one neutral exist. And a variety of methods are permitted to be used for grouping these circuits together, such as cable ties, wire markers, tape, or other similar means. Also associated with multi-wire branch circuits is the requirement that they must have a simultaneous disconnecting means, and circuit conductors, grounded and ungrounded, must be grouped. So we discussed that in the previous slide. This particular requirement is again addressed in Article 210.4 B and D. And the simultaneous disconnecting means is typically accomplished by a single breaker tie bar, or toggle, sometimes it's called, which connects both of the circuit breakers together. This slide shows just a simple diagram which shows a couple of situations, or at least one situation, where you've got a multi-wire branch circuit, and you can see that you've got black, red, and blue conductors that are going into 3 separate breakers, and all 3 of those breakers are tied together with a tie bar. In addition, all of those wires, all 4 of the wires, the 3 ungrounded conductors and the 1 grounded conductor, or the neutral, are all wire tied together, again, so that any maintenance personnel can quickly identify which conductors are associated with which circuit. The photo on the right here depicts exactly what we as inspectors would prefer to see. Neat, organized, clear, clean installations. All of these single pole breakers are fed by different phases of the 3-phase 4-wire main. And of course, standard is black is L1, red is L2, and blue is L3. So those are the 3 phases of a standard 3-phase 4-wire supply. Neatness and organization counts with respect to electrical installations for several reasons, the primary of which are, number 1, it enhances safety. There's no question that when you've got nice, clean, neat installations, especially where you've got energized circuitry, that it is more safe for all service, maintenance, and repair personnel. Additionally, it promotes clear communication to the installers about what is going on in the panels or in the boxes or in the components that are associated with these electrical circuits. I'm sure that all of you have noticed in the last few years the increase in the number of electric vehicle charging systems, identified sometimes as EVCS. Outlets are required to be supplied by a separate branch circuit for EVCS systems or EVC systems. This is discussed in more detail in Article 210.17. It goes on to say that a minimum of one 125 volt, 15 or 20 amp receptacle outlet must be installed within viewing distance or sight of, which is identified as 50 feet max, of the electrical service equipment. This is reiterated in Article 210.64. There is additional information for electric vehicle charging stations provided in the California Electrical Code, Article number 625. There are some new 2019 California Electrical Code amendments relating to EVCS, and I would encourage you to review those as needed, and as you verify that a project that you've been assigned to does in fact include electric vehicle charging systems in the scope of work.